Okay, in this video we're just going to take a minute and introduce chemical bonding to you. In short, chemical bonding is the bonding between atoms of elements through electrostatic attraction over the valence electrons. So when we talk about chemical bonding, we're talking about how atoms are sharing or transferring valence electrons between the atoms. Let me give you some examples. So we're talking about ionic bonding. We're looking at a bond between metals and nonmetals. If you can remember from a previous video, we talked about on the periodic table, family 1 and 2, we call those like the alkali or alkaline metals. They easily want to lose electrons. It helps them achieve their stability. For example, lithium, if you look at the periodic table, it has an atomic number of 3, meaning it has 3 total electrons. Here's lithium's nucleus. The first energy level has 2 electrons, and it has 1 outer valence electron. And remember, every atom is trying to achieve stability, and what that means is it wants its outer energy level to be completely full of electrons. Well, in this case, it's easy for lithium to lose that 1 valence electron. So right now it's neutral, but not stable. Once it loses this 1 valence electron, what's it look like? Well, it's going to be positively charged. We now call that an ion. But now it's going to look like this. Here's its positive nucleus. The first energy level will have its 2 electrons, and that would be its outermost energy level. Here, the outermost energy level was the second energy level, and that's a certain distance away from the nucleus, and that distance is a specific amount of energy between the nucleus and that electron. And it just simply means this electron spends a large amount of its time in that particular distance from the nucleus. Once it loses that, now its outermost energy level is that first energy level, and it has 2, and now it's stable, so it's charged, but now it's stable because it's lost that 1 valence electron. Well, it's not going to just randomly lose one. That's going to be transferred to somebody else. So in this case, this metal from family 1 could bond with, let's say, fluorine. Fluorine is part of family 17. It has 7 valence electrons. And it will be the recipient of this 1 valence electron. Okay, what does that look like? Well, here's fluorine's positive nucleus. Its first energy level will have 2 valence electrons. Its second energy level will have 1, 2, 3, 4, 5, 6, 7. And notice, for fluorine to become stable, it wants to receive 1 more valence electron. Well, who's that electron going to come from? It's going to come from lithium. So once that 1 valence electron lands here with fluorine, I'll darken that in, fluorine now becomes stable, but it's also charged. In this case, instead of being positively charged by losing an electron, fluorine becomes an ion. It becomes negatively charged as a result of receiving that 1 valence electron. It'll be a 1 negative charge versus the lithium being a 1 positive charge. And this attraction, electrostatic attraction, forms what we call an ionic bond, a bond between metals and nonmetals. And the chemical formula, since it's just a 1-to-1 ratio as far as the atom's concerned, the chemical formula is just going to be LiF. And if you were to just look at that chemical formula, you should be able to look at a periodic table and recognize lithium is a metal from family 1. Fluorine is a halogen from family 17. What do I have here? A metal and nonmetal. It's actually a bond between ions. I dissolve this in water, it would dissociate into ions, positively charged atoms. So it gives you an idea of ionic bonding. Let's talk about covalent bonds. If ionic bonding involves a transfer of electrons, covalent bonding is going to involve sharing of electrons. We're sharing valence electrons. For example, let's look at hydrogen. Hydrogen atomic number is 1. It has 1 valence electron. Now, you might recall it's in family 1, so you might think, wait a minute, isn't that a metal? Well, it turns out it is in family 1, but hydrogen is a nonmetal because there's its 1 proton in the nucleus, and at first energy level, it has 1 electron. While it has the potential of losing that electron, really to become stable, it just needs to gain 1 more electron because it only takes 2 electrons to fill that first energy level. So say I have a bond here between hydrogen and oxygen. You look at oxygen, here is its positive nucleus. Oxygen has 8 total electrons, so 2 go into first energy level. And in the second energy level, we have 2, 3, 4, 5, 6. Well, it's almost like they work out a deal. Basically say, hey, how about if I share one of my electrons, and if you share one of yours, and together we will be stable. So the positive nuclei of each atom is going to mutually attract. These electrons are going to be shared. But bonding only occurs if everybody becomes stable. So we're going to need 2 atoms of hydrogen here. So here's another atom of hydrogen, and it's 1 electron. And this is how we get the water molecule, H2O. We're going to need 2 atoms of hydrogen to bond with 1 atom of oxygen. Let me redraw this so it looks a little more clear. So 1 atom of hydrogen. Here is its positive nucleus, and it's going to share that 1 electron here. And this particular hydrogen, here's its positive nucleus, and it's going to share its 1 electron here. And so if I were to draw circles to represent those electron clouds, it's going to look like this. And you can see there that those 2 electrons in between these 2 atoms are spending the majority of the time between these 2 atoms. Redraw that, looks a little more symmetrical here. So here's my 2 hydrogens that are sharing these 2 electrons, satisfying its energy level requirement. And oxygen now has its 8 electrons, filling that second energy level. All right, so this would be an example of covalent bonding. But it's really unequal sharing, because if you look at an oxygen atom, it actually has more protons in its nucleus than hydrogen. So there's more of a positive, more of an electrostatic attraction on those electrons. So literally those electrons are going to spend more time closer to the atom of oxygen here. And that gives what we call a polar covalent bond. And it's just a simple reference to the fact that it's an unequal sharing, and it creates a slightly positive charge on the ends of these hydrogens. If I actually draw the structure of this a little bit more clearly, I'll show you. Here's the oxygen atom. Here's the 4 electrons that are not being shared by hydrogen. And here's the electrons that are being shared by the hydrogens. It's got a bent nature to the structure of this water molecule, and the reason being is because these unshared electrons are negatively charged. They repulse the other ones. But we add these little subcharges. These hydrogens are slightly positive charged, and this side of the water molecule is slightly negative. but they're still sharing electrons. It's not a equal sharing of the electrons, so we use the term polar covalent to represent. Now if I write a chemical formula for that, I'm writing H2O. And that's what I want to transition here finally to end this video, is just briefly talk about chemical formulas. This here, we call that a subscript. This tells you how many atoms of that particular element we have to bond with this element. So when we write chemical formulas, it's a representation of how many atoms of each element are needed to make that one molecule or one compound. Let's look at a few examples and then we'll be done. Let's take a look at carbon tetrachloride, CCl4. So the 4, we call that a subscript. And when I look at this tells me right away I have 4 atoms of chlorine bonded with 1 atom of carbon. Let's make sense of this. So if I start with carbon, I know that carbon has 4 valence electrons. I can look at the periodic table. I see that it has an atomic number of 6. That means it has 6 electrons. 2 of those go in the first energy level, leaving 4 for the second energy level. In a previous video, we talked about the patterns of valence electrons in each of those columns on the periodic table. So I could simply draw that like so, just showing that this particular carbon atom has 4 valence electrons. And this chemical formula tells me in order for this bond between these 2 elements to happen, I need a ratio of 1 to 4 or 4 to 1. And so what that looks like is if I bring in these 4 chlorines, that's what I have here. Chlorine is in the halogen family. It has 7 valence electrons that I'm representing with these little circles, and the one that it's sharing. So if I look at this particular electron cloud, chlorine has all of its 8. If I look at this particular electron cloud, that chlorine has its 8 in the second energy level. Same with this one, same with this one. But also, what do you notice? This carbon has all of its 8 as well. Okay, and you can see, what is this? This is a covalent bond. Okay, let's look at this in the reverse sense. Let's look at, okay, so if I'm going to create a bond between elements, how do I know what the chemical formula is? In this example, I went from the formula to the structure. Now let's look at just a periodic table and how do we write the chemical formula. So let's use the example of, let's say we have a bond between magnesium and fluorine. Okay, so I look at the periodic table. Magnesium has an atomic number of 2. I'll put AT number 2. And fluorine's atomic number is 9. So right away I want to start thinking about the number of valence electrons. For magnesium it's 2, and for fluorine it's 7. My next train of thinking is, okay, this is a metal, and this is a nonmetal. And that should already start triggering your thinking that this is going to be an ionic bond and there's going to be a transfer of electrons. All right, so how many? Well, magnesium wants to get rid of 2. So its ion charge will be a 2 positive, meaning it's going to lose 2 valence electrons. Fluorine's ion charge will be a negative 1. It wants to gain 1 valence electron. All right, well notice this isn't a perfect ratio of number of atoms between the 2 elements. All right, so if magnesium wants to get rid of 2 valence electrons and 1 atom of fluorine can only take 1, I'm going to need a second fluorine atom to receive the second. Okay, so to visualize this, magnesium's giving away 2 electrons. Fluorine can only take 1, so I'm going to need 2 fluorines. Right? So my chemical formula is going to be MgF2. Being careful to write my 2 as a subscript. So I need a number of atoms of each element that make sure all the transferring or sharing of electrons are accounted for so that each element is complete.